Okay, this P7 video is on the basic properties of lenses and what lens power is and how it can be altered. So we need to know about the two basic lens types, and in fact you only need to focus on one of them for the syllabus. We have convex or converging lenses, where the surface of the lenses kind of slope outwards, and also if you only have one lens surface that slopes outwards and bulges like this and another surface that's flat, that counts as converging as well, or convex. And the other type is concave or diverging lenses. Now, for the purposes of our study, we only need to concentrate on convex or converging lenses, and we're not going to look at concave or diverging lenses at all. Okay, so the question then is, what does a convex or converging lens do? And we also need to be able to explain it in terms of refraction, which we looked at in a previous video. So let's start off by looking at a basic diagram. So we have a lens here, and we have something called the principal axis, which is basically a line through the middle of the lens, sort of at right angles to the plane of the lens. And then we have some light rays coming in, and what a lens does is it takes parallel light on one side of the lens and focuses it to a point on the other side. And there are some distances we need to be able to label on here. Okay, this plane here is called the focal plane. It's at right angles to the principal axis, and it's where the light from parallel rays on the left-hand side of the lens will come to a focus on the right-hand side. And the point where the focal plane meets the principal axis is called the focal point. And what you can see is that the light rays here, which are parallel to the principal axis, will come to a focus at the focal point on this right-hand side. There is also a focal plane on the other side of the lens, which would obviously be useful if the light was coming from the other direction. So this is kind of symmetrical here, and the two are at the same distance away from the plane of the lens here. So we call the distance between the plane of the lens and the focal plane the focal length, and again we can label it on the other side as well. And we've discussed these basic things, that what the lens does. So that's the basic layout of a convex lens and the terminology we use to describe the points on this diagram. In a separate video we're going to look at how we can use some basic rules about how the lens refracts light in order to draw ray diagrams. We're not going to cover that here, we're just talking here about the basic properties of a lens and what it does. So that's what the lens does, it brings parallel light to a focus. You also need to really be able to explain how the lens does that looking back at refraction, because all we've done here is we've put the light in and we've got a magic line in the middle of the lens that changes the direction of the light. Now obviously that's not what's really happening. Whilst on this diagram we've drawn it changing direction in the middle of the lens has got two surfaces, so it's going to change direction at the two surfaces. It's fine to do this version for any ray diagrams you're drawing, but if you're trying to explain how the light is brought to a focus by the lens, then we need to use the proper description of the refraction. So we're just going to take in the next slide a look at the red box section here zoomed in, and a look at the two rays that we've drawn and what actually happens to them as they go through the lens and how that causes them to converge in the focal plane after they've been through the lens. Okay, so let's do that now. We've zoomed in on that section of the lens. We're going to look at the ray at the top first of all, and there's the path it actually takes. So it changes direction at the front surface of the lens and the back surface of the lens. And again, you can see these two normals, and this looks remarkably like the prism from before. It's not quite the same because I haven't had the ray come in at an angle. It's coming in horizontal. And as a result of that, this tilting, again, in the same direction both times because of the relative tilt to the normals here that are drawn in red, means that that basically skews the ray clockwise in both cases. Okay. Now the key thing here is that if the center of the lens is down off the bottom of the screen here, but very far from the center, the orientation, the direction that these two surfaces are in, are quite different from each other. They are tilted from being parallel. What that means is that the effect on the ray is greater. It will be refracted more because the surfaces are tilted more. And correspondingly, we look at the ray that is near the center of the lens, then it will be refracted less because the surfaces near the center of the lens are not very tilted toward compared to each other. They are closer to being parallel. Okay, so what you can see that's done is that the ray at the top here is now heading towards the principal axis much more a much steeper angle than the ray at the bottom here. You can see that they are converging. So all we need to do then to make sure our lens works properly is for it to have this basic property of bulging in the center. And if we want to get to work properly, we need the right shape of the two surfaces in order to make sure that rays that are parallel on one side all come to a focus at the same point on the other side. And that's where the difficulty in making the lenses come. The engineering of getting this surface to exactly the right shape is quite tricky, and that's partly what makes lens making quite expensive. They've got to be ground down to exactly the correct shape. Okay, so that's the explanation for how the lens is able to refract to produce a convergence of the parallel rays on one side of the lens. We also need to understand what the power of a lens is. Now, this is not anything to do with electrical or mechanical power. This is an entirely separate concept. Electrical and mechanical power are linked because they're both rate of energy transfer. This is nothing to do with rate of energy transfer. This is purely to do with how much the lens can bend the light that comes through it. And so we define the power of the lens as 1 divided by the focal length, so the number 1. And the focal length for this needs to be in meters in order to get the lens power in diopter. There are no other alternate units. And for any of you who have prescriptions for glasses or contact lenses, the numbers on the prescription are the power of the lenses you need in diopter. We won't go into the fact that there's pluses and minuses on the prescription. That actually refers to the two different types of lens we discussed at the top, and since we're only dealing with one type, it's not really important to worry about that. But in case anybody was wondering why you've got pluses and minuses on your prescription, that's basically related to short and long-sighted, which require the different lens types to correct them. Okay, so because of this equation, power is inversely proportional to focal length. As we increase the power, we'll decrease the focal length and vice versa. And the basic idea with that is that a lens with greater power will bend the light more, and if you think about what that means, if the light is more bent, it will come to a focus closer to the lens. Okay, so it's been bent off course more, it will come to a focus at a point that is close to the lens, and so the focal length will be reduced. So just a quick example calculation then to see how this works. It's fairly straightforward. The only thing to watch out for is units, really. So what is the power in diopter of a lens with a focal length of 20 centimeters? Well, the trick here, of course, is that we've been given centimeters and not meters. So the first thing we need to do is to convert the centimeters to meters. So 20 centimeters is 0.2 meters. And then the power of the lens is just 1 divided by 0.2, so 5 diopter. Okay. The last thing we need to know about here then is what we can physically do to the lens in order to change its power. So if we want lenses for a particular application, and therefore we want lenses with different powers and different focal lengths, how do we go about getting that? This is going to be very important when we look at the telescope later on, where the magnification of the telescope is going to depend on the focal length and the power of the lens. Okay, so let's look at the two factors we need to know about then. The first of which is what we call curvature. So curvature is just basically how curved the surface of the lens is, and also relates therefore to how thick the lens tends to be, because to get a greater curvature you need to have a greater thickness. So if we look at a lens with high curvature and think about what we said when we talked about what actually caused the lens to bring the rays to a focus in the first place, it's the tilt of the two lens surfaces relative to each other. So high curvature gives us a large tilt, and what that tends to mean is we've got a high power and a short focal length. That high curvature lens will make the rays from the left hand side converge closer to the lens. And if we have a low curvature lens, so a sort of thinner, flatter surface to the lens, then it has a low curvature, a lower power, and thus it doesn't affect the direction the rays are travelling as much, and we get a longer focal length. This is the reason, by the way, that in old sort of glasses in particular, if somebody had a very strong prescription, they would have to have very thick lenses in the glasses in order to get it to work. Now, the second factor we need to consider explains why modern sort of glasses don't need to have very, very thick lenses, even to get a very sort of powerful prescription in there with a high diopter. The second factor we need to look at is the material the lens is made of. So advances in materials and being able to manipulate the refractive index that we mentioned sort of kind of previously is what enables us to have very thin lenses in our glasses these days, but still have them be very powerful. So we could have a thin lens, but with a very what we call high refractive index material that is still able to to change the direction of those rays a lot and therefore focus very close to the lens with a high power. And we can have a different material with a low refractive index, the blue one here, where the same shape of lens will still give us a longer focal length and a lower power, just because we have a different material in the lens. Okay, so that's the lens basics of lenses, including factors that can affect the power of the lens and how to do the power calculations. Watch out for a separate video where we're going to go through the idea of ray diagrams, so how to draw a ray diagram for lenses bringing light from stars to a focus, how to draw a ray diagram for lenses looking at objects that are what we call extended, like the moon, and also the functioning of a telescope and how that works.